Unit Operation Classroom, Gate 2023, Question 25. A liquid surge tank, this is a surge tank, which surge tanks are usually used to dampen inlet flow rate oscillations. So that's a surge tank, so that there's even if there's a large oscillation in the incoming flow, that flow out becomes much smoother. So that's basically a surge tank. Has F in and F out, has inlet and the outlet flow rates respectively, as shown in this figure. F out is proportional to the square root of the liquid level, which normally happens if there is a gravity drain out, and then the F out becomes F out is F out is proportional to square root of H. The concepts of fluid statics we have seen before. The cross-sectional area of the tank is 20, this cross-sectional area is 20 centimeters square. Density of the liquid is constant everywhere at steady state value. So when steady state means when F in is equal to F out, and at that point, the steady state value of the height of the liquid in the tank that is given, which is 16 centimeter. The variation of H with Fn is approximately first order transfer function. So we have to assume a first order transfer function model. So which one of the following is the correct value of the time constant tau? Okay, this problem has been solved in a textbook. I have given a detailed of the textbook. Uh, and the details are given in the website here. So this problem has been solved in the textbooks, giving all the steps, and that's where this comes from. So this is the transfer function where how much the height changes corresponding to change in the flow rate. That's given by this particular equation here, where tau is equal to R1A, where R1 is given by this. So we know the value of the steady state height. Only thing we don't know is the C. That can be obtained from the steady state value, which is given. It is given as the flow rate out is proportional square root of H. So we assume this to be a constant. So F out at steady state is given, and the corresponding value of H is given. So we can calculate the value of C. So once we put the value of C here, we know the value of HS. We can calculate the value of R1, and from there we can calculate the value of tau, and that becomes 64 seconds. All the detailed calculations have been shown in the website. So this C is the correct option. Now, you can stop the web video here, but if you want to understand a little bit about chemical engineering application, so this is a very important problem because normally, let's say in wastewater equalization tanks, there's a large variation in the flow from the process plant coming from different sources. These come to the wastewater treatment plant before there is a wastewater equalization tank to smoothen out the flow that goes to the wastewater treatment plant. So there's a highly unsteady flow. So tau, the time constant of the system, is really given as area divided by this derivative, which basically means how for just one unit change in the height of the tank, one unit change in the height of the tank, how much the flow rate changes, outlet flow changes. So this is the definition of the tau. We can how that is done. We can see that again through deviation variables. We know F out is C square root of H. As I said, this is very standard for the gravity flow and maybe flow through an orifice. So these are very standard equations proportional to the square root of the height of liquid in the tank. So since this is non-linear, we have to linearize it using Taylor series expansion around the steady state point. So it's operating at the steady state point. What happens? There's a slight deviation, positive or negative. So this is the one we neglect the higher derivatives here. So we do that. So this is what is given here. I'm shown the details, so that's what it comes out. So this particular derivative comes out to be, once we substitute the value, comes out to be 5 over 16 centimeter cube per second. So the unit is centimeter cube per second. So basically what happens, so for every unit change in the height, so 1 centimeter change in height, the flow rate, outlet flow rate changes by 5 over 16 centimeter cube per second. That's what this derivative is. And of course, the time constant is this. So as you can, this volume and this volumetric flow rates are related. So that's basically, as we know, is the time constant. So so once we know that, and if we substitute this value, if substitute this value here, we know area is 20 centimeters square. We can get the value tau is 64 seconds, which we have uh, seen before, right here. So what are the implications of these values? Let's say if there's a small tau, you just look at these definitions here. Small tau, this value small means this value must be very high. This value very high means that if the slight change in the height of the tank makes a very large change in the flow rate out of the tank, right? So there's what happens is a high outlet sensitivity. So that's very fast draining of the system. And the large tau, just the opposite, that's a low outlet sensitivity. So we have a tau is approximately slightly greater than 1 minute, which is moderate sensitivity. And from control point of view, this appears to be okay. So anyway, so the answer C is correct.